Hello and welcome to this very important laboratory, the Respiratory System Laboratory, exercise 7 on PhysioEx, Respiratory System Mechanics. And we will be doing today activity 1 titled Measuring Respiratory Volumes and Calculating Respiratory Capacities. So before we measure the respiratory volumes and before we calculate the capacities, let's look at this conceptual illustration first to define our respiratory capacities and respiratory volumes. And then we will be looking in more detail into this very detailed long volumes, quantitative long volumes and capacities illustration. So conceptually, let's look at this middle line and let's call this equilibrium. So that's at 0. And to the right of this line, we have all the gains that would enter into our lung. So everything to the right of this line is air going in, positive air, air that I'm gaining into my lung. To the left of this middle equilibrium line is all the air that I'm supposedly losing. So tidal volume, you see it has 2 arrows because tidal volume, first of all, it has to be at rest. There is no tidal volume under any form of force. So tidal volume is the amount of air that tidal volume is the norm in normal breathing. It's the amount of plus 500 milliliters of air that you can inspire, bring into your lung, or the minus 500 milliliters of air that you remove or you expel out of your lung when you expire. But you cannot add both. You cannot add 500 milliliters of air going into the lungs and then you add 500 milliliters of air that are leaving the lung. That doesn't make sense. So it's either or. That's why it has the absolute value. The tidal volume has an absolute value of 500 milliliters. So that's the tidal volume. I go up 500 milliliters of air coming into my lungs, and I go back minus 500 milliliters of air leaving my lungs. Now, the thing is, if I take a deep breath and then I force extra amount of air into my lungs, yes, the lung can do that. It can take more air, forced air into the lung. That is known as the inspiratory reserve volume, which is the extra volume of air that can be inspired beyond the tidal volume. So it begins after the plus 500 milliliters that I brought in. I'm bringing in extra. How much can I bring in? An extra 3,000. So my inspiratory reserve volume is actually 3,000 milliliters after the 500 milliliters that I brought in. And when I add the volumes, the 500 milliliters that I brought in as my total volume to the inspiratory volume, the inspiratory reserve volume of 3,000, 3,500, that would be my IC, my inspiratory capacity, which is the sum of my tidal volume and my inspiratory reserve volume. That is very important. So now we have identified our tidal volume. We have identified our inspiratory reserve volume, and we have now also identified that the sum of my tidal volume and my inspiratory reserve volume will give me my inspiratory capacity. Now, let's move on. On the other side of the spectrum, my expiratory reserve volume, it's the inverse concept of inspiratory reserve volume, which is the extra amount of air I can forcefully expel out of my lungs following my expiratory tidal volume. So I take a deep breath, I breathe like when I'm relaxed. So this has to be a relaxed, normal breathing pattern. So I take in a 500 milliliters of air into my lung, then I bring out 500 milliliters of air. Then I immediately after the minus 500 milliliters of air that has left my lungs as a tidal volume, normal breathing, when I bring out a lot of the maximal amount of air I can bring out, that would represent my expiratory reserve volume. So the expiratory reserve volume is the maximal volume of air that can be expired beyond the normal tidal volume expiration. And that comes out to 1100. So my inspiratory reserve volume is 3000, but my expiratory reserve volume is 1100. So 1100. Now, there is something known as the residual volume. The residual volume is the volume of the air that lags behind, and that what keeps my lung inflated, and that what keeps my lung fluffy and full. So the residual volume is the volume of air that lags behind in the lung after the most forceful expiration. So after I remove my expiratory reserve volume, this residual volume, I can never get it out. It must stay behind and lag behind to keep my lungs from being deflated. And we talked about the inspiratory capacity, which is the sum of my tidal volume and my inspiratory reserve volume, and the expiratory reserve volume plus this residual volume that lags and stays behind. If I add them together, that would give me my functional residual capacity, and the vital capacity is going to be the sum of everything except my residual volume that lags behind. So my expiratory reserve. So when I take a deep breath and remove all, so when I take a deep breath in tidal volume, then I take extra the maximum amount of air I can bring in after my normal tidal volume that I brought into my lungs. Then I expire everything out. That would include my expiratory reserve volume. The sum of all of that would be the vital capacity. Vital capacity does not include my residual volume. That is very important. There is the total lung capacity, and that includes everything. I'm sorry, I have not identified it, but you know that the total lung capacities are always multiple volumes, and that includes multiple volumes and capacities. So the total lung capacity would include my inspiratory reserve volume, my tidal volume, my expiratory reserve volume, plus my residual volume. Total lung capacity, I can represent it with volumes and capacities. I could say my total lung capacity is my inspiratory capacity plus my functional residual capacity. So I can mix and match, but it has to fulfill this conceptual diagram. Total lung capacity is the maximum volume to which lungs can be expanded with the greatest possible force, which is as we said, the vital capacity plus my vital capacity plus the residual volume out here. Okay, so now let's look at it number-wise. So my residual volume is 1200 milliliters. So I must begin from 1200 milliliters. That is the amount of air. So the functional residual capacity is 2300 milliliters. I'm sorry, 2300 milliliters. So right here, 2300, that is my excuse me. So this functional residual capacity is what keeps my lung, as we said, inflated, and that what I'm sorry. So that functional residual capacity is what keeps my lung inflated, prevents it from being deflated. So if I need my tidal volume, it has to be above that. So my tidal volume right here, that represents from 2300 up to 3000. That should be around approximately 500 milliliters. That's my total volume. That's my tidal volume. Then my inspiratory reserve volume is going to be above my tidal volume. So I take in 500 milliliters, and then the extra amount that I can bring in is from 3000 up to 6000. That's about 3000 milliliters. Then you can just see, for example, the vital capacity is going to be the sum of my expiratory reserve volume, which is this much. So you can look at this diagram and do the math. This diagram is more precise. This is a conceptual diagram to let you have a conceptual understanding of these volumes, what do they represent, and these capacities, they are the sum of which volumes and which capacities. But this diagram is just excellent to show you precisely that this functional residual capacity is the air that lags behind, and it's about 2,300 milliliters, and the tidal volume is from 23 up to 3,000, almost 500 milliliters, and then the inspiratory reserve volume is usually from 3,000 to 6,000, that's about 3,000 milliliters. So now you can get a precise number of what do they expect. So when we do the experiment and we're measuring our vital capacity, for example, we should know that it's from, for example, 1,200 milliliters up to 6,000, and then we just subtract. That's about 4,000 and 4,000 and 700. But we will see exactly. This is just important for us to understand these concepts. Another concept that we have to also understand is the ratio, the FEV1 divided by the FVC. So FEV represents forced expiratory volume. So what happens is this is part of the pulmonary function test. So a patient will be asked to take a deep breath in, and then in this one represents 1 second. And then the patient will be asked to expel all of the air that was taken in. So the patient will be asked to take a really deep breath that would include my tidal volume and inspiratory reserve volume, which is the inspiratory capacity. And then the patient will be asked to expel everything out, remove all the tidal volume and the expiratory reserve volume, and then in 1 second, we will measure how much came out. So the FEV1 represents the amount of air that you can quickly and forcibly exhale in 1 second. It has to be within 1 second after a maximal inhalation. And the FVC is going to be the amount of air that you can exhale after the maximal inhalation. So I take a deep breath in with a maximal inhalation. And then this is not time. The FVC is not restricted with time. So the FVC is usually 5 liters. But the FEV1 is timed. That's why we call it 1, because it must be confined to 1 second. And then usually healthy patients, they are able to expel 4 liters out of the 5 liters that they have taken in. And that ratio, 4 divided by 5, that comes to 80%. Now we have two types of patients. We have the OLD, the old, which are the obstructive lung diseases, and there are also restrictive lung diseases. In obstructive lung diseases, what happens is the major problem is that the patients cannot get the air out due to the loss of the elastic recoil of the alveoli. We see this with emphysema. So there is a collapse of the alveoli. They have no problem taking air in. So the air will be flowing in obstructive lung disease. So we would have a vital capacity. But when we want to expire, the air is not coming out. So there will be a drop. Obviously, there will be a drop, and then that ratio is going to drop from 80%. So we will notice that in the first second, the forced expired volume will be reduced severely. But the forced vital capacity obviously will also be reduced, but it will not be reduced as severely as the expiratory volume in that 1 second. So that will cause the ratio to drop, but it will be reduced and it will be less than 70%. That's why emphysema is diagnosed with a FEV1 over FVC ratio that will give us a number of 60% or less. In restrictive lung diseases, now it's reversed. In restrictive lung diseases, I'm no longer dealing with obstructive lung disease in the sense that the air can enter, but it cannot exit. Here, it's the opposite. Air can exit fine. In restrictive lung diseases, like in fibrosis, it's not emphysema anymore, it's fibrosis with restrictive lung disease. What happens here is air can leave fine, but it cannot get in. So the problem with patients who have restrictive lung diseases, such as fibrosis, what happens is air cannot get in, but it can get out fine. And that is represented by FEV1 that is reduced, but the FVC is going to be reduced even much more severely. So that, how does that affect the math? What affects the math is there is a drop on the numerator, which is the FEV1, but there is an even more drop in the denominator, which is the forced vital capacity. So the overall math, that what happens is you will not see an overall drop in the ratio because there is a severe drop in the denominator. What happens is you may see even an increase in the ratio. So you would see about, so in normal patients, we would have 80%. You would have an 80% ratio. But for patients who have fibrosis or restrictive lung disease, you would have even more ratio, about 88%. So there will be less air coming into the lungs, and that would affect all the volumes. So if I have less air coming into my lungs, if I have less air coming into my lungs, that means the tidal volume will be less, the inspiratory reserve volume will be less, the expiratory reserve volume will also be less, that the total lung capacity will be less. So everything is going to be less because I am lacking air that is entering into my lungs. So let's go back into the lab and things will make more sense as we perform the lab. So let's click on activity 1. Activity 1's objectives are to understand the use of the terms, what is ventilation, what is inspiration, what is expiration, what is the diaphragm, what are the external intercostal muscles, what are the internal intercostal muscles, the abdominal wall muscles, we will talk about them. And then there's the expiratory reserve volume, we talked about that. And then there's the forced vital capacity, tidal volume, and then there's the forced expiratory volume in 1 second, and we will see all of that in detail. So in an introduction, the two phases of ventilation or breathing are inspiration and expiration. So inspiration, during which air is taken into the lungs, and expiration, during which air is expelled out from the lungs. Inspiration occurs as, so this is very counterintuitive because for both, for inspiration and expiration, we use intercostal muscles, but we don't only have one type of intercostal muscles. We have external intercostal muscles and we have internal intercostal muscles. Inspiration begins with an N. So you may assume that in inspiration, we use internal intercostal muscles. No, we use external intercostal muscles in inspiration. So in inspiration, it is the external intercostal muscles and the diaphragm that would contract, and they would contract in order to expand the volume of my transverse diameter of my rib cage and to increase the chamber of my thoracic cavity. And when I increase the volume, the pressure is going to drop and fluid, air fluid would enter from the atmosphere into my lungs nicely and smoothly. And also I have abdominal wall muscles that would help when they also would contract and to help pushing and in expiration. So when I'm expiring, you see that I'm no longer in expiration. We're not using external intercostal muscles. We are using internal intercostal muscles all the time, but we're using intercostal muscles all the time. But in expiration, we are using internal extracostal muscles that push against my lung to deflate the lung. We describe the tidal volume. We described the inspiratory reserve volume, the expiratory reserve volume, residual volume. We talked about all of these volumes and capacities. So now let's talk about the lab. And we have to have a very good understanding of the forced expiratory volume. in the first second. That's why it has a 1 next to it. It measures the amount of the vital capacity that is expired during the first second of the forced vital capacity test. And the equipment we're going to use are going to be simulated human lungs, and there's a rubber diagram, a rubber diaphragm, an adjustable airflow tube, and there's an oscilloscope, and there are 3 different breathing patterns: normal, tidal volume, expiratory, reserve volume. Well, let's get into the lab. Before the lab, we have a couple of pre-lab questions. Which of the following statements describes the mechanics describing the mechanics of breathing is false? So which one is false? Ventilation refers to the movement of air into and out of the lungs. That is very true. Ventilation is measured as the frequency of breathing multiplied by tidal volume. That's also true. Ventilation includes the process of inspiration and expiration. Also true. Ventilation relies exclusively on contracting skeletal muscles. No, so that we relax. So when I am inspiring, I'm bringing air in, I am utilizing my external intercostal muscles contracting, but I'm relaxing my internal intercostal muscles. So it's not only contracting, we relax some other muscles. So the contraction of which of the following muscles will increase the thoracic cavity volume during inspiration? So the contraction of which of the following muscles will increase the thoracic cavity volume? So if I want to increase my thoracic cavity volume, that means I want to make the pressure less. And if I want to make the pressure less, that means I'm trying to bring in air from a higher pressure, the atmospheric air, into the pressure of my lungs, the interpleural pressure. So that means I'm trying to inspire. So if I want to inspire or inhale, that means I'm using my intercostal muscles. And when I'm using my intercostal muscles, when I'm inhaling, that means I am contracting my external intercostal muscles. So the contraction of which, yes, the external intercostal muscles are contracting. At the beginning of inspiration, the diaphragm relaxes. In inspiration, I'm trying to bring air in, so that means I want to make the volume bigger and the pressure less. So the diaphragm would not relax, it would contract. The thoracic cavity volume must increase. That is true. At the beginning of inspiration, the thoracic volume must increase to make the pressure less. The diaphragm becomes dome-shaped. If it becomes dome-shaped, that means it's moving upward like a dome, compressing my lungs, making the volume of the lungs smaller, and that means the pressure is going to be higher, and then air is not going to flow in. That means I'm expiring. I'm not inspiring anymore. That's wrong. The thoracic cavity pressure would increase. So the thoracic cavity pressure would increase if I want to. That is not true. So it must be a thoracic cavity volume increases. Okay, at the beginning of expiration, so when I'm expiring, what happens is here my diaphragm is going to be dome-shaped. It's going to be compressing against my lungs with the help of my abdominal muscles, and also I'm going to be utilizing my intercostal muscles, and I'm going to be contracting my internal intercostal muscles. So that means the pressure, the thoracic cavity must increase. That's very true. And the abdominal muscles relax. No, they will be contracting. The volume of the thoracic cavity would increase. If the volume of the thoracic cavity increased, that means the pressure would decrease, and that means air would go in. So that makes it inhalation, not exhalation. That is wrong. External intercostal muscles must contract. If the external intercostal muscles contract, that means I'm inhaling. That is wrong. So it has to be the first one. A tidal volume refers to the amount of air inspired and then expired with each breath under resting conditions. Now, let's get into the experiment. So, okay, so we have simulated lungs, and that's airflow and airway radius. So note that the airway radius is set to 5 millimeters. We're going to modulate that. So we know that the flow of fluids is directly proportional to the radius to the power of 4, whether we're dealing with liquid fluid like blood flowing into the blood vessels, or we could also be dealing with air fluid moving into these airways that are not blood vessels. They are airways. So note that the airway radius is set to 5, but we can change that up and down. So select the start to initiate the normal breathing pattern and establish a baseline or control normal respiratory volumes and capacities. We're going to observe the spirogram that develops, so this is the spirogram that develops on the oscilloscope, and note the simulated lungs breathing on ventilating a tidal volume as the result of the contraction and relaxation of the diaphragm. So this is going to be my diaphragm. Let's click start. So you see that shows me my tidal volume. Air coming in, air getting out, air coming in, air getting out, air coming in, air getting out, air coming in, air getting out for 10 seconds, 20 seconds, 30 seconds. So this is my independent variable, the time on the x-axis. On the y-axis is going to be my dependent variable, and that is we're going to represent my lung volume. So this is my tidal volume. So now if I take a deeper breath, the time is still going to be the same, but the volume is going to increase because now I have inspiratory reserve volume. Then I'm going to have expiratory reserve volume. So that's going to be changing a lot. So let's record the data. So that shows us the radius was of my airways is 5 millimeters. The flow unit volume per unit time was about 7 liters and 7.5 liters per minute, or 7,485 milliliters per minute. My tidal volume was, as I expected, so I expected from this diagram here, 500 milliliters. So that makes a lot of sense for me. 500 milliliters, my tidal volume. And I have yet to, this was just my control. I have yet to do expiratory reserve volume because this is just normal breathing. I haven't forced anything inward or outward. Never forced anything inward. I'm just here. I'm doing this. Tidal volume, up and down, up and down. I'm taking in 500 milliliters. I'm taking out 500 milliliters, as shown here. You see, up and down, up and down, up and down. So now let's move to the next phase. So now it says select clear tracings to clear the spirogram on the oscilloscope. So we clear the tracings, and then you will now complete the measurement of the respiratory volumes and determine the respiratory capacities. So first, so now we're going to be doing volumes and capacities. Select start to initiate the normal breathing pattern after 10 seconds. So when we hit the 10-second mark, as measured on the oscilloscope right here, select ERV. So now we're going to click on expiratory reserve volume to now make the lungs take in additional or expel out expiratory reserve volume. So we're going to be expelling out maximal amount of air, and then we're going to wait for another 10 seconds, and we're going to click on FVC, which is going to represent forced vital capacity, to complete the measurement of the respiratory volume. When you select the ERV, the program will simulate forced expiratory forced expiration using the contraction of the intercostal muscles and abdominal walls. And when you select the FVC, forced vital capacity, the lungs will first inspire maximally. Let's go to FVC. So the forced vital capacity. So my forced vital capacity, which represents the vital capacity right here, it's going to be the sum of my expiratory reserve volume, my tidal volume, and my inspiratory reserve volume. So everything, so the vital capacity is everything right here. The forced vital capacity is the same thing as the vital capacity. Forced vital capacity in experiment is going to represent for me those three minus the residual volume. It's going to be the expiratory reserve volume plus the tidal volume plus the inspiratory reserve volume. So let's do that. So now press start. In 10 seconds, press FVC. When it hits 20, now press FVC, and then we have taken all the measurements. So now we have recorded our tidal volume, our expiratory reserve volume, our inspiratory. You see now it labeled it so nicely for me. That is the tidal volume, that is the inspiratory reserve volume, that is the expiratory reserve volume, and this is my residual volume that lags behind, and these are my vital capacity and total lung capacities. And let's click on record data, and now we have recorded everything. Now, it's a couple of questions. Which muscles contract during quiet expiration? So when I'm expiring, remember we said
Either way, we use intercostal. We use internal intercostal muscle. We use intercostal muscle. I'm sorry. We use intercostal muscles. But when I am expiring, I use internal intercostal muscles. So I contract my internal intercostal muscles. Which muscles contract during quiet expiration? So the muscles, when I'm expiring, I contract my internal intercostal muscles. I use intercostal muscles either way, but now I have to determine, is it internal or external intercostal muscles? If I'm expiring, I don't use X. When I'm expiring, I don't use external intercostal muscles. When I'm expiring, I use internal intercostal muscles. And I also use the help of my accessory abdominal wall muscles that push. These abdominal wall muscles push against the lungs to expel or expiate all of the air out. So this sounds like which muscles contract during quiet expiration. I'm sorry, this is quiet expiration. So none of the muscles contract during quiet expiration. So in quiet expiration, I have the passive diaphragm responsible. But when I'm doing my forced, when I'm doing my forced expiration, it is my abdominal wall muscles and my internal intercostal muscles. They are the ones who contract, force out this when I am doing this, when I'm doing the expiratory reserve volume, when I'm expiring everything out. That is with the additional help of my internal intercostal muscles and abdominal wall muscles. Okay, let's move on. Now, minute ventilation is the amount of air that flows into and then out of the lungs in a minute. And that is going to be calculated by tidal volume times breath per minute. So using the values from the second recorded measurement, enter the minute ventilation in the field below and then click submit data. So let's go into our data. Our breath per minute were 15 and our tidal volume is 500 milliliters. So let's multiply 500 times 15. 500 times 15. That comes out to 7,500. And submit data. Okay, predict question. Lung diseases are often classified as obstructive and restrictive. An obstructive disease affects airflow. Obstructive disease, air is welcome to come in, as in emphysema, but it can never leave due to loss of elastic recoil. And the restrictive disease, what happens is the air cannot, due to fibrosis, cannot get in, but it can get out normally. And that, both of them, they change and they affect my volumes and capacities differently. So although they are not diagnostic, pulmonary function tests, such as forced expiratory volume in the first second, can help. So that's the ratio we talked about, can help a clinician determine the difference between obstructive and restrictive diseases. Specifically, and in the first second, the forced expired volume in the first second is the forced volume expired in 1 second. So in obstructive disease, such as chronic bronchitis and asthma, airway radius is decreased. So when when I decrease the radius, I know that the flow of gas fluid will drop. So what happened in the ratio is air comes in, but it cannot go out. So my FEV will drop significantly. So when it drops significantly, the ratio is going to decrease proportionally. So that is going to be the right answer. So now we're going to be exploring. You will now explore what effect changing the airway. So we're going to look at the airway, changing the airway radius on pulmonary function, on the pulmonary function. So these are the dependent variables. So we're going to decrease the airway radius. So that's going to be my independent variable that I'm going to be changing. I'm going to be decreasing it. And then we're going to be looking at its effects on the on these volumes and capacity. So these are the dependents. These are the dependent variables. So now let's do that. So now you will explore you will now explore what effect changing the airway radius has on the pulmonary function. Decrease the airway radius to 4.5. So from 5, we go to 4.5. So now let's do every 10 seconds, we're going to be utilizing expiratory reserve volume and our vital capacity or forced vital capacity. So at 10 seconds, we're going to click on ERV. And at the additional 10 seconds, we're going to click at 1. So click start, 10 seconds. Then in another 10 seconds, we're going to click FVC, and now we are finished. So now we're going to measure all of these variables after we have decreased our radius to 4.5. Record data. So now repeat this step until you have tested an airway radius of 3. So we have done it 4.5. Let's do 4 now. Start. 10 seconds. Another 10 seconds. And then FVC, and we are done. Let's do it again now. Instead, we have to do it until we are at 3 millimeters. Let's record the data for 4. Now let's do 3.5. Start. When we hit 10, ERV. When we hit another 10, FVC. And then we're going to record the data. Record data. Now let's do 3. Start. Then FRV. Then FVC. Then record the data. This is an amazing table. It shows us the effects. Okay, so a useful way to express FEV1 is as a percentage of the forced vital capacity, which is another name for our vital capacity, using the FEV1 and FVC as a ratio from the data grid. So calculate the forced expired volume in the first second as a percentage by dividing FEV1 volume by the FVC volume, in this case, the vital capacity, and then multiplied by 100. So enter the forced expired volume in the first second for an airway that is of a radius 5. That's the control here in the field below, and then click submit data. So what I'm going to do is we're going to find for radius 5 what was in the first second. It was 3541, and the vital capacity was 4791. And then we're going to multiply by 100. So let's divide 3541, calculator. 35, that's 3541. Was it 3541? 3541 divided by 4791. 4791. That comes out to 7.73 times 100. That comes out to 73%. That comes out to 73%. I know from my lab that it should have been 80. It should have been 80. But if it drops below 80, that makes it obstructive lung disease. If it goes above 80, that makes it restrictive lung disease. So now I'm no longer getting 4 liters out. I'm getting even less than 4 liters out. So let's say 73%. Submit data. Now let's do it for 3 now. So we're going to compare the 2 spectrums, 3 and 5. So FEV1 is 436, vital capacity 621. Let's divide 436 by 621, multiply by 100. 436 divided by 436 divided by 621. 621. That comes out to 70%. Severe drop. So the more drop, the worse it is. So that comes out to 70%. Submit data. Okay, congratulations, you completed the experiment. Submit. Submit. Okay. To calculate a person's vital capacity, you need to know. So now for vital capacity, that's my vital capacity or forced vital capacity. The vital capacity, I must have the three: IRV, inspiratory reserve volume, tidal volume, expiratory reserve volume. I need those three. Let's see, what do I have? It says I need tidal volume, expiratory reserve volume. What's missing is IRV. I need that one. This is supposed to help. So I need IRV, I need ERV, and I need TV. Those three will give me my vital capacity. So when I add them up, add 500 to 1200 to 3091, it'll come up to this number. But we already know it, we don't need to calculate. So, okay, measuring a person's vital capacity means that you are measuring the amount of air remaining in the lungs. No, that's the residual volume, the sum of VC and RV. Is it the sum of VC and RV? No, that's the total lung capacity. The amount of vital capacity that is expired in one second. No, that is FEV1. So that makes this divided as the amount of air that can be expelled when the subject takes the deepest possible inspiration, inspiratory reserve volume, and then forcefully expels everything out as rapidly as possible. Going to be the amount of air that can be expelled when the subject takes the deepest possible air, yes, and then expels everything out. Yes, that's true. Next, measuring a person for vital capacity in the first second means that the sum of VC, the amount of vital capacity expired in the first second. Excellent. A person suffering from an asthma attack, inhaling medication are expected to, so here the flow has dropped in the asthma attack. So what I need is I need to increase F directly proportional to R to the power of 4. So I need to increase the volume. In order to, when I increase the volume, I reduce the resistance. That's true. I do not reduce the volume. No, if I reduce the volume, I decrease the oxygen supply. I decrease air coming in. I decrease my lung capacity. I don't need to reduce the total lung capacity. That's detrimental. That's against my cause. And I do not need to reduce that. I need to reduce the resistance. Which of the following values, does not include ERV? So I know that ERV does not include ERV. Okay, so vital capacity must include ERV. Total lung capacity will include everything, and the tidal volume obviously is not part of the expiratory reserve volume. Submit. Okay, what would be an example of an everyday respiratory event where there is expiratory reserve volume? When I expire more than my tidal volume, like when you sneeze, achoo, what you do is you are expiring more than the tidal volume. So sneezing is good. Okay, what additional skeletal muscles are utilized in an expiratory reserve volume? How about the abdominal wall muscles? So when remember when the question that I got wrong is because when we are forcing things, we're no longer only relying on the diaphragm. We use internal intercostal muscles and abdominal wall muscle. Okay, what was the FEV percentage in the initial radius of 5? So let's go to 5. The initial was radius of 5. We're looking for percentage, so that means I must divide the 3541. I must divide 3541 by what is my vital capacity? By this 3541 by 4791. I think 3541 by 4791. It was 73. That shows you this patient has definitely an obstructive disease. Okay, question number 4. What happened to the FEV1 percentage as the radius of the airway decreased? So as the airway of the radius decreased, you saw that there is, as the radius decreased, you see that the FEV1, when we compared, it was 5 to 3, it has decreased proportionally. Okay, lung diseases are often classified as obstructive, affect airflow, and restrictive usually reduces volume, and restrictive disease reduces volumes and capacities. Okay, obstructions. Okay, we have answered that. Explain why. The results from the experiment suggest that there's an obstructive rather than restrictive, because there's an overall drop in the ratio. There is the FEV1 percentage decreased proportionally as the radius decreased, while this is the characteristic of obstructive pulmonary disease. There's a drop, so we no longer have 80%, we have less than 80%. Okay, and these diagrams just show us what happens baseline, and that's when the radius was 5. And as the radius drops, you see that all the capacities and volumes just significantly drop. They just significantly drop. Okay. And okay, that's the end of the lab. I'll see you in class. End.